Thanks, Stephen. My name's Andy Vickerstaff. I'm a Senior Rail Interface Engineer for Transport for London now. This is all going to be about London Underground, so please don't ask me about the other bits yet. Hopefully I'll be able to come back and tell you sometime. This is really going to be about the challenges of optimising things on a system that is this old and built by the Victorians. Unfortunately, the Victorians had great foresight with drains by the Bazalgette sewers, not so much with the railways. This is a section through Baker Street, part of the original tunnel, now 155 years old, where we were still running steam trains. 45% of it is underground, bit of a misnomer, the underground, when 55% of it is above ground. But the original tunnels, like the one we've just seen, were built by cut and cover, take out the road, put the track back in and put it back over. So that's actually the embankment, I think. You see St Paul's in the background. That was also a sewer as well, which I imagine was fun. And 35% of it is what we call deep tube. So once we had gone away from steam trains and put in third and fourth rail and electrified, we could suddenly build tubes deeper, and therefore they were less disruptive to build. Unfortunately, they were also built very small, so you can see the kind of clearances we're talking about. Things like ventilation are often not very good, so operating diesel plant in them. Some places you can, other places you can't. And what are we most famous for? Mind the Gap. This is Waterloo Station on the Bakerloo line. That's about 140 metre radius curve, which is not only a nightmare to maintain, but for stepping distances, it's also very interesting. So, sub 200 metre radius curves, people talk about curvatures. Sub 200 is what we would call tight. 1,000 metre curve is a straight as far as I'm concerned. And you'll see why. So, this is just a quick overview of the real map. So if you look down, basically the older it is, the curvier it will get. So you see the original district, Met lines. Central line is always an interesting one, basically running under Oxford Street, but it's got two enormous curves at Bank, which is one of our biggest problems, and this one up here, which is called the Caxton curve, which is basically where we test everything to destruction. It's a 70 metre radius curve. Originally was just supposed to go in the depot, but then someone decided not to do that. And also, we've now got modern demand. You know, this is Night Tube that started operating 2 years ago. Obviously, that has had a slight impact on the tonnages, but more than anything, what it has an impact on is you've lost your Friday and Saturday nights. Saturday nights were always the one to do your highest risk jobs, change your turnouts, all that kind of stuff, because you got longer, you got a later start up on a Sunday. So currently on 6 lines, will eventually, I imagine, post-upgrade of the subsurface network come everywhere. So we have to plan a lot better. Just to give you an idea of some of the tonnages we are talking about. So this is just subsections, tonnage. So 2011 as a baseline and then up. So this is Green Park to Victoria, the Victoria line. By 2028, we'll have a 57% increase, nearly 50 million gross tonnes a year. That's what happens if you run 36 trains an hour. They don't have to be very heavy. Jubilee line, 43%. Northern line, up about 51%. But the big one, which I'm going to talk about in more detail, is really on the subsurface network. So that's Farringdon to Barbican, which I'm going to talk about. But because there we're going from 20 trains an hour to 32 trains an hour, but that's where we have 8.5 tonne axle loads versus the deep tube where we're looking at 5 tonnes. So, being wheel rail interface, I have to talk about wheels first, I'm afraid, so bear with me. So my team started measuring wheels about 3 years ago because I didn't really believe what I was being told. And funnily enough, so this is the blue line, that's what a new wheel looks like. This is the worst one we found. The red one, which is a hollow tread of 4 mil. So at 2 mil is where the standard is, because that's where you lose all your coning angle, so the wheel stops steering. So we were finding 4 mil, and therefore we started looking at some wear rates. So this is for the 09 tube stock, which operates on the Victoria line, so very intensive service. And you can see on the x-axis, you've got the kilometres run. On the y, it's coming down. This is the hollowing. You see they're both reasonably linear. You can argue there's a bit of a kick up at the end. But you'll also see there's two very distinctive lines here. That's because the 09 tube stock, 3 out of 4 cars in the unit have motored axles. The final one doesn't, so it's all tread braking. And therefore, all our wear rates are way up here because we're not doing any regen or rheostatic braking. It's a real problem for the maintainer because you've got 2 completely different turning regimes, and then that means you've got 2 completely different overhaul regimes. And when you're running 36 trains an hour, you need a lot of trains in service. From a wheel rail interface perspective, what we're really interested in is what are the wheels that are running around on the track. So this is a distribution effectively in sort of half mil bands of hollowing and percentage of wheels in service at any time, with a pre and post, pre before we got hold of it, and post after there's now a preventative turning regime at 150,000 kilometres on the trailer wheels and nearer 250 on the trainers, which we'll come back to see why that's important to know what shape the wheels that are running around are. What are our next biggest challenges? We've still got a lot of this. Those of you who are old enough will know what this is. This is Bullhead rail with fish-plated joints every 18 metres on wooden sleepers. I can't remember where this is, so don't blame me, but it's a nightmare to maintain. It's very loud as well if you want to go into the noise and vibration. And we still, about 60% of the network is now being converted to flat bottom, but about 40% of the network is still in Bullhead because we can't get it out quick enough. So in terms of broken rails, what are we looking at? So this is a line by line. Well, this is a year by year, broken down by line. So you see we're sort of averaging around 10 to 11. I can't remember whether that was a particularly cold winter. It had a bit of a spike. This is in the financial year, so not many. But you'll notice that there's a few that stand out. So Northern, Piccadilly, bits of the Victoria line. That's because they've got the biggest proportion. So this is our broken rails by flat bottom versus Bullhead. So you can see the Bullhead 54, this is since 2013, and 54 rail breaks in Bullhead and 6 in flat bottom. I think that tells its own story when you think that only 40% of the network is Bullhead, yet it accounts for 90% of your rail breaks. What's the biggest issue with it? Well, often the failures are around the joints. With fish-plated joints, it comes often from down here, which is fish plate fretting, where as the bolts start to loosen, the joint starts to move, you start to get fretting, you get cracks like this. They go up to the bolt holes and then back up to the running table. Unfortunately, this is very difficult to detect ultrasonically, especially if you get one in the middle, you might get a chance, but if it comes from the field or gauge side, you won't see that. And you're reliant on visual inspection in a tunnel in the middle of the night, in the dark, to try and look for that, which we're getting better at, since it's been highlighted, but it's still very difficult to manage. In terms of defects, this again is by year, running at about 2,500 probably on average. Again, you'll notice there's probably some that stand out more, Jubilee, Northern, Central, and that is because they are all dominated by these things, which is squat-type defects, sometimes called studs, where we believe, and there's lots of published literature out there about looking at wheel slide protection activity that generates martensite, where these small cracks can develop. We actually leave a lot of them in the ground now. We monitor them. They don't tend to grow, so we will take them out eventually, but it gives the maintainer time. We let them build up until it's easier to re-rail than try and weld repair individual squat-type defects. But it still dominates our wheels. So a few years ago, we started looking at different techniques, obviously increasing tonnages, increasing defects. How can we much better monitor them? So first of all, we introduced, this is B-scan, ultrasonic technology. It's exactly the same as A-scan, but the difference is you can record what you're seeing. Most of the analysis is now done offline, so it'll be gone out, tested, and then the next day people will go through, highlight artifacts, go back and verify and action defects. You got quite a big bow wave as soon as you brought it in on every line, because we were finding stuff that was better, but we like to find stuff early. You could do something about it. It doesn't turn into broken rails. We also brought in 2013, this is the MRX rail surface crack measuring kit. This is a magnetic flux system that's designed specifically to measure the depth of RCF, which ultrasonics is not very good at because it's too near the surface. So it magnetically magnetizes the rail and measures the flux that comes back, and from that we can get a measurement of the depth of RCF up to 7 mil deep. Doesn't go any deeper than that. Okay. So I'm going to talk you through a case study, really, which emphasises some of the challenges that we have about optimising wheel-rail interface. This is Farringdon to Barbican on the Metropolitan line, again part of the original tunnel. What you can see here is this is what the driving technique diagram, so they're manually driven at the moment. Currently a project called 4LM, which is upgrading all the signalling system. Eventually this will be automatic train control. We'll go to 32 trains an hour, but at the moment that's what the drivers are supposed to drive to. But what you'll notice is this is a very short section. This is about 300 metres between Farringdon and Barbican. Currently we're actually putting in a new sidings that goes around the back here between the two. That's how short it is. And you'll see that it's got a lot of signals in it. And a lot of them have got R's. I'm not a signalling expert, but I know that means repeater, because this is a 180 metre radius curve. So it's incredibly tight going around the corner, and because we're still driving on line of sight principles, there are repeaters that tell drivers what's going on around the corner. You'll also notice it's all uphill. So a renewal was carried out here about 2 years ago, off the top of my head, and we saw very fast degradation of the rails that went in. A double junction has also gone in now as well on the 180 metre radius curve. And we were asked to look at it in terms of looking at the rail condition, and the first thing we discovered was that this is a sample of train driving speeds, where effectively the orange line is what the drivers are supposed to drive to, but this is just a sample of what they actually drive to, which is probably how you would drive your car around a blind corner where you think there might be a red light. So you can see they power up round the corner and wait to see what the repeater signals are going to say, and then drive very slowly round the curve. Unfortunately, this curve is designed for 40 kilometres per hour operation, and any of you who will have measured RCF, looked at RCF, know that Cant Deficiency is very good in preventing RCF, and unfortunately what happens is a lot of these trains down here are actually Cant deficient. Even at the 40 kph, they would only be just deficient. However, one of the issues with having short station sections is that's just the front of the train. So the back of the train can be going at 40 kph. So you're designing for such a range of speeds over a very short section that the current curving rules currently being looked at to see whether we can make some improvements to allow that deficiency. So this was the state of some of the rails. So this is at one of the repeater signals where we noticed, obviously we've got low rail corrugation, check rail on the low rail. We've now currently changed our standards. That probably would not have a check rail. Not that I think it would make much difference here, but you can see we've got RCF, corrugation, which is where the two combine, where you get in the troughs of the corrugation, you start getting spalling, breaking out from the RCF, which, although the RCF actually is very shallow, sometimes it makes the rail untestable, and therefore we have to try and get in there, hand grind it, which doesn't do a lot for the profile, to make it testable. So this is a mini profiles of the low rail, just through the cycle, just to show how it deteriorated. So if you see the blue, that's our brand new target 56E1 profile. See, as low rails tend to, they like to flatten. And this is post-grinding. This was ground about 2 months ago. So we're monitoring this site very carefully. And what the next slide, this is just to explain one of the measures. There's lots of ways of measuring rail profiles. One of the things that we look at for low rails is we started looking at what our crown radius is. So that's effectively telling you how round the top of the rail is. And this is a measure of that. So you can see on the tonnage and then the crown radius, as the rail's deteriorating, we're getting a reasonably linear trend. And then hopefully post-grind, we get back to restoring our crown radius. But that's actually often the driver for how much we have to grind, because we have to take so much material off that rail. The actual high rail where we're trying to remove RCF in the gauge corner is not the driving factor. This is. So this is the monitoring that's also done while we take the profiles. We look at it under magnetic particle inspection, and we try and have a look at the RCF. So you can see it's at 49 million gross tons. Sorry, these pictures always look really good on my screen. I'm not sure they ever come out that well. But you can see how there is one band of cracks developing at 49 million gross tons, just in the gauge corner, which is fairly typical of what we see. And then at 88, as this rail's getting flatter, you see we've still got this original one, but now we're starting to see a couple of other bands of RCF developing. And then this is 90 million gross tons post-grind, where you can see the grinding marks where we have removed enough material. There are some cracks back in it. I believe, and this is what we'll come to, is that I think these are new cracks. They can develop that quickly. That's the number of cycles we're talking about in 2 million gross tons. So this is some of the simulations. So we carry out vampire vehicle dynamic simulations, and one of the things we're looking at here is contact position. So this is where we come back to needing to know what all our wheel profiles look like. So if you imagine this is just down the track, so from 0 to about 350. This is the distance from the gauge corner where the contact is, and this is for a range of profiles, so in the half mil hollowing. So what you can see is at 44 million gross tons, all our wheel profiles are still pretty well in that band where that first band of RCF developed. Although you'll notice these ones out here, these are the ones that are approaching the limits at 2 mil, where we start getting some vehicle instability. But come 88 million gross tons, you can see all that movement has moved away from the gauge corner, and that fits pretty well with those two bands of cracks we're now seeing. You'll also see their wider distributions. So on the high rail, one of the things we did, the high rail, as you saw from the pictures, deteriorated pretty quickly. At the time, we'd just approved HP 335 rail, British Steel's premium rail product. So the maintainer said, can we have that on the high rail? We said yes. So again, slightly difficult to see. This is tonnage of the two rails, the 260 and the 335. Again, this is just area lost. It's another way of measuring rail wear. We could do it in many ways. But you can see at the moment, the 335 isn't necessarily showing anything particularly great in terms of wear performance. It's a 180 metre radius curve. It will wear. I like wear. It's predictable. But what you'll see is the biggest difference is down here is where this is the 260, where you're starting to get a lot more plastic flow down at the bottom of the lip, whereas the 335 is actually staying pretty consistent with the shape. So this is the high rail contact position. So we looked at the low rail before. This is the high rail. I haven't plotted the range of wheel profiles because really what we're looking at here is two types of RCF, as you'll see from the pictures. But again, this is the distance from the gauge corner of the contact versus the distance along the track. And what you see, this is the leading and the trailing wheel set of the bogie. So you can see the leading wheel set's right up in the gauge corner, as we'd expect. Trailing wheel set is actually not sitting, is sitting pretty much near the gauge corner, but pretty much in the middle of the gauge corner. And that is where we will see our bands of RCF developing. So again, this is the high rail in 260, the high rail in 335 at the different tonnages. You can see in the 260 we had this band of cracks developing pretty quickly, and by 49 million gross tons they're just starting to break out. I would say this is totally undetectable by the rail surface crack measuring kits because it's less than 0.5 mil deep, where the algorithms can't quite handle it, so we really start to use that at 1-2 mil depth. But you'll see in the 335 at similar, getting up to similar tonnages at 40 million gross tons, we've got nothing. But the key thing for us in terms of what we're looking at from modelling is that we can now differentiate. This is now, we know the trailing axle of the bogie that is putting these cracks in, whereas the leading one is causing wear down here. Why is that interesting? Well, when we started measuring RCF, we started trying to model it to get some better predictions. This is something called the whole life rail model, which was developed by Network Rail, or their predecessors as was, following Hatfield, to try and predict generation of RCF. So what you've got on the x-axis is what's called T gamma. That's a product of the creep, or the force, times the slip. So think of it as a measure of all the energy in the contact patch effectively. And then this triangle was developed empirically to give you a damage factor. So what this says is that below about 15 for 260, you don't generate any RCF. Then you start to generate RCF only up to a peak, and then you start to bring some more wear in it, and the wear and the RCF balance themselves a bit more until you go over the threshold and you should be in wear totally. The red line is for what was proposed for HP335 in an RSSB study. It's never really been taken forward and validated, but we know that we've seen plenty of improved RCF performance. So again, these are some of those results from the modelling that says on the high rail. Well, this is our leading axle, the green lines for 260 and 335. You'll notice it's negative down here because it's basically saying we're in wear. We should never generate any RCF in the gauge corner, and that's pretty in line with what we see. But up here, we've got our trailing axle in the middle of the railhead, and at 260, it's saying we're right at the peak of that triangle in developing our RCF. But in 335, we should drop down. It's saying we're still going to generate RCF, but at a lower rate, which is pretty consistent with what we're seeing. Back to my favourite topic on Cant Deficiency, and this is really modelling the same site at some different speeds to look at what the difference is. So you'll see that basically, again, this is just for that trailing axle, so that RCF that's being generated in the middle of the railhead. So at 40 kph, which it's designed for, where we've got about 30 mil of deficiency, we're looking at down here. Interestingly, between the 20 and the 30 that I modelled it at, you actually probably just peak yourself over the top of that triangle, because from 20 to 30 it goes down. But see what the track was designed for is where we want to be. So this is some results from some generics. So as I was saying, I don't really consider anything up here a curve, although the number's quite high, but they drop off pretty quickly down to that 1,000. So the green line is the leading axle predictions of that RCF for 260, for the leading one, which is the solid line, and for the dash one, which is the trailing one. And this is curve radius damage factor. And this is for the 260 and for the 335. So just again illustrating that hopefully, if the predictions are right, we should be reducing our RCF generation with the 335. But it's really down here, we've got to get into our sub 200 metre radius curves before we're generating that trailing axle RCF in the middle of the railhead. And again, we should be reducing that rate. So we currently have about 60 monitoring sites like the one I've talked about across the network. And what we're really seeing here is that this on the left is a 400 metre radius curve we're monitoring, and on the right is a 200. So what you can see on the 400 is we're not generating any of that RCF in the trailing axle in the middle of the railhead, but we're generating plenty of cracks down here in the gauge corner. When we go down to the 200, you'll see there's a blue area, which I've used to illustrate that this again is moved back into that wear area. There's a little orange line in the middle, which if you notice the angle of the cracks is very different. So gauge corner cracks classically at the 30 to 40 degrees, whereas these cracks are at 90 degrees to the direction of running. And we could show that in the simulations by showing the force angles that we're generating. But there's this little orange bit in the middle, which I think is, if we simulate it further, we'll probably show that as that rail wears and that contact moves over on the leading axle, we'll start generating those cracks at a different angle. So say we've got about 60 sites, because really what we're trying to do is take that model, validate it against our network, and try and look at developing our grinding regime really to try and ensure we are an RCF-controlled railway. I won't ever say an RCF-free railway. I don't think that's possible. So we are trying, at the moment, this is just a ranking that we did with the 60 sites we've got, so sort of saying no cracks when we start to develop cracks, and then these ones, which I've described as the breaking out spooling, which is where we really want to be grinding between these two, because this stops it becoming untestable. So this is a bit of a shotgun, and the proper scientists in here can argue about the numbers, but I could plot about 8 different best fit curves through those lines if I wanted to. But really what we're trying to do is generate a radius versus tonnage and say, where do we want to be? This one down here is that Caxton curve, which I talked about, so that's quite an extreme. I'd almost probably take that out. But you can see that if we look again back at our whole life rail model predictions, there's probably a sort of steady state down here, 200 being a bit higher, and then once we're getting up here, we shouldn't generate any RCF cracks in the gauge corner or in the low rail, because this is a combination of low rails and high rails as well. So once we introduced the HP, it went in quite a few places, and in some places worked very well, in other places it is not. This is a site between Liverpool Street and Bethnal Green on the central line, where it's a 400-metre radius curve on NTF 415 concrete sleepers with the 92 tube stock running on it, which equals corrugation for us. So it's a well-known noise complaint site. So it went in HP, but also you'll notice it's on a resilient track fixing called Pandrel Vanguard, which is designed to isolate that ground-borne vibration. That broken rail occurred at about within 15 million gross tonnes on the low rail. And what we found when we took it out of the ground was that you can see, if you look at broken rails like I do, you'll notice there's a very short brittle zone, a very fast fracture. So the whole rail has gone very quickly from quite a small crack. And when we looked at the rest of the rail that was taken out, we found these cracks. This crack is less than 0.5 mil deep. But you'll also notice it goes straight down, which we'll come back to. So these cracks that we generate in the centre of the railhead from that trailing axle, what the issue seems to be is that they start to spall. These photos courtesy of British Steel, I would say, on the right. So this is that rail that we've seen before. But you'll see how they often start to spall because they come down and then join back up. And then that's when they tend to break out the surface. In the 335, you can't see it, but it seems more vulnerable to these ones coming straight down. This is one of the reasons. Again, these photos, thank you to British Steel. So this is your, what people would call classic RCF gauge corner cracking at that 30 to 40 degree angle against our 90 degrees, which comes straight down. And since I did these slides, we have actually started measuring some rail deflection, because we thought that was probably one of the key factors. And what we found on the Pandrel Vanguard sites is we were getting about 3 mil vertical deflection down, as opposed to on some of the other sites where it was more 1.5 mil. But also what we noticed was that it was also going back up. So we were effectively putting the top of the rail into compression and tension, which we think has exacerbated it. That's still to be looked at in more detail, because we only measured one side of the rail, so we're not sure whether it's roll or whether it is inflection back up. But it seems to be vulnerable to not so good track. So the final element of wheel rail interface that I'm just going to touch very briefly on is about adhesion rationalisation. When I started the wheel rail interface team, it was all about wear. That's what we failed through. We had older trains with fixed frame bogies that ripped curves to pieces. Now, since we've got more flexible frame bogies, better steering, wear is becoming less dominant. We've got lots of these out there still, but we've taken out about 75, I think, in the last 5 years, where they were on radius curves where we no longer need them. And we're moving to this, which is an onboard system where we have both top of rail and gauge corner on the train. Why? We get less access. This is a lot easier to maintain. It's a lot cleaner, and you can control it much easier. We will never get down to, we've had sub 200 metre radius curves where lubricators have been left off. You will never do that on these alone because of the noise alone. Doesn't matter about the wear performance. But we were trying to reach a point where we know what we need to apply where. And we're going to get a new train at some point. I'm not going to comment any more on that. So this is my final epitaph. If you take only one thing away from this talk, is that these are suitable uses for Bullhead rail. This is the Blenheim and Festiniog Railway. You'll notice it's not actually on the track. That's all flat bottom, but for bracing structures, that's fine. This is the Harrow on the Hill car park. That's fine. What it is not fine for is running 40 million gross tonnes a year on. Thank you very much.